Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 7. In the last section we were talking about the different crystal defects, which could be point defects, line defects or surface defects, and then in context of that we had observed that how the presence or absence of a particular lattice site filled with a particular atom of either the same species or different species makes a difference in terms of inducing crystal defects. We also saw that if several such atomic spacings continued over a long line are together able to move or together able to pack in a more denser fashion, it would result in something called a line dislocation. We further observed that if there is a sudden change in the direction of the crystal or there is a discontinuity in the way that the crystal was proceeding, this normally happens between zone 1 and zone 2 observed by two different lines called the twin planes. It is normally known as the surface defect, and so in context of that we also saw that for a multigrain structure you can visualize these surface defects or what we call twin defects formulated generally within the surfaces. Today we are just going to investigate a little bit of numerical values for does the material property really get influenced because of these different dislocations moving in a lattice matrix, and as you will see that there would be a heavy influence of the defects on the material properties. So let us look at first the elastic and plastic deformation within crystals, and you know that most of the conventional manufacturing processes, particularly the secondary level processes like machining etc., involve the deformation of the work material. So let us look at atomistically what happens. So in the absence of any external force, the distance between let us say there is a pair of atoms which are there and they are separated by a distance d, which is also the equilibrium distance, we call it dE for example. So atomistically in the absence of any external force, this d is because the balance of all the forces acting on the atomic system which are spaced with this distance d is 0. Okay, so there are obviously going to be forces of attraction between the electrons and the nuclei, and there are going to be forces of repulsion between the two different nuclei, and so all these forces acting in a balanced manner would create an equilibrium situation where the lattice spacing is considered to be d. Okay. So let us look at the net interatomic force. So obviously in order to hold these atoms together at a distance d, you need some amount of force for doing that, and this net interatomic force here is non-zero as you can see at the distance d. And supposing under the application of an external tensile force, the interatomic distance increases beyond d to maintain the equilibrium. So we apply an external tensile load, let us say P, okay. Then the interatomic distance should be, let us say, some value dA, because now because of the external applied force there is going to be a change in the lattice spacing, okay, between the atomic system. I am only talking about a biatomic system at this time. I am not concerned with how the atoms get arranged in a crystal, okay. So then the interatomic distance should be dA, so that the interatomic force becomes an attractive force of the same magnitude, so that it can take the configuration back to the equilibrium distance d once the force P is removed, so the tensile load is removed. So it should just go back or take back the distance of separation between these atoms in the atomic system to be d from dA. So the question is, does it happen for all different spacings dAs, or is it governed by some limitation where there is a finishing of the the effect of one atom on other beyond a certain cutoff distance, etc., which would not lead as such the dA to get converted into d. Okay. So, if dA is not very much different than d, let us say of the order of 5%, then upon the removal of the external force, the atoms would attain more or less their original position. But similar thing would happen in a compressive force. Obviously, compressive force, the dA, the actual distance because of the application of that external force would be lesser than d, and so when you remove that force, then there has to be repulsive forces generated in the system, which will take the system back to its equilibrium distance d. But this is only limited to about 5% change in d, but beyond 5% the distance is so much that the influence of the primary atom finishes, and then the system may not restore back to normal conditions. So, this 5% d or increase in the distance is something which you can probably recall as the elastic region of the material, but beyond this d, if the atoms displace more than the distance 1.05 d, let us say, then you have what you call a plastic range or a flow deformation, plastic flow deformation. So, having said that, let us look at let us consider a very primary model where you consider a crystal lattice with regularly spaced atom as shown in the figure below right here, and you are having an external force influencing just it is a shear force, as you can see, and the shear comes probably along this plane right here, because the upper portion is being moved by the force towards the right and the lower portion towards the left. And so, when the applied force reaches a sufficiently high value, the crystal lattice would look something like this, right, like in the figure 1.20b, where all the atoms are in equilibrium and will remain. Thus, if external force is removed and there is a permanent deformation is produced in the crystal lattice. Okay. All the atoms are in equilibrium and will remain thus if external force is removed, and thus a permanent deformation is produced in the lattice crystal, or this permanent set deformation, the fact that the crystal does not come back to the normal regime, this is known as the plastic deformation, and it cannot be recovered even after the withdrawal of the external load. Okay. So, this is like more like if supposing this slip happens of one plane over the other by some distance, this is known as the and it is non recoverable, this is known as the plastic deformation. So, that is how you can understand that what atomistically is happening when we refer to different regions. So, let us look at some of the associated values related to the amount of, let us say, the shear stress which is needed vis-a-vis the amount of deformation which would be executed because of the shear stress. Shear stress obviously, as you know, is force per unit area, shear force per unit area. So, let us next find out the amount of shear stress necessary to affect the slip between two layers of atom, and this is across the shear plane, which actually moves the upper half of the lattice with respect to the lower half of the lattice, as you had seen in the last figure. And this is more you can say that this is in a perfect lattice, which does not have any defects, point defects, so on and so forth. So, this is just a sort of a theoretical analogy of what may happen. So, as a first approximation, the shear stress tau and the amount of movement of the layer x can be related to each other mathematically. Let us look at how. So, think of it that this is the atomic system that we are talking about, and x is the distance which is being moved from a position which was equilibrium position. Okay. And because of this movement, and this movement is executed basically because of the shear force. So, obviously, let us say this was the old position, the dotted one was the old position, and this is the new position, and you are moving at x distance. So, if you look at really the crystal structure earlier, this is the equilibrium position, and so is this. So, basically the atom, let us say over the shear plane, is exactly at equidistance from the atomic pair which is below the shear plane in this particular case. So, this is the 0 condition where all the forces are 0, because of which the atoms stay in equilibrium distance with respect to each other. Think of the analogy we did in the last slide. Here, when you move it from this equilibrium position by a distance x, there is obviously going to be some forces which are going to interplay, and these forces would, the cycle of the forces would continue, the net forces would continue unless and until the dotted portion comes to the let us say to another kind of a position. Let us say this atom comes to a position where this exactly is at the center between this particular distance between these two atom pairs, so that it can formulate similar kind of equilibrium as you saw before. Okay. So, the position here again has 0 forces, the position in the center here from which it started had 0 forces, and in between there are going to be some forces where at least halfway through this whole atomic movement by a lattice spacing A, there should be a sort of a force getting it back to the previous position, and for the later half of this A there should be a force which would get this atomic system back to the later position. That means the later position is that this atom really comes all the way to this center place here in this particular figure as shown here, where the equilibrium forces or where the net forces are 0 and it is another equilibrium position. So, how will you describe it mathematically? So, if I say that the variation of the tau, that is the shear stress which the crystal is giving out in opposition to what is being given to it from outside, is actually equal to tau 0 sine of 2 pi x by a, then it serves the purpose. Let us look at it. When x equal to 0, obviously the tau is going to be 0. So, therefore, there is no shear stress given back by the crystal. If tau is equal to, if x equal to a by 2, in that event the amount of tau is again equal to 0, because now it is in a position where again in the central position where it would really have equal amount of the positive and the negative forces, and beyond this. So, basically tau is 0 again. If x is a, then again the tau becomes equal to 0. So, these are probably the positions over which the atomic system is going to be happy. Okay. So, obviously between the x equal to 0 to x equal to a, the force would be as if the crystal can come back to the initial position, and between a by 2 to a, the force would change directions, and it will be as if the crystal can go to the final position, where as I told you, this circle, the dotted circle right about here, moves to this center position here, where there is again equilibrium condition. So, in between obviously there is a condition which is shown here by the solid line, where the forces between these two atomic systems would be equal to 0, and it will also be in equilibrium. So, at a by 2 also there is going to be a net stress given out by the crystal which is equal to 0, and it is going to be in equilibrium. So, this is actually represented by this condition. Obviously as you see here, x equal to 0, tau is equal to 0, x is equal to a by 2, tau is equal to 0, and x equal to a, tau is equal to 0 again. So, we basically talk about a sine wave of wavelength a, where a is actually the lattice spacing, concerned lattice spacing. So, once we have done that, we are enabled to sort of see what is going to be the stress strain relationship given this shear stress value with respect to the position x of the layer above the shear plane with respect to the layer below the shear plane. So, we are going to, for small values of x by a, make a small assumption here that tau is tau 0 2 pi x by a. Okay. So, the sign is converged to 2 pi x by a, and therefore, the shear strain produced in such circumstance if we assume the total vertical spacing between the lattice to be equal to b at this time, let us say this unequal lattice spacing, which seldom happens because in a crystal you have more or less regular orientations of the atomic planes with respect to each other, whether you go in the vertical or horizontal really does not matter, and the lattice spacing is one constant a. So, b is actually equal to a for the regular kind of crystals, but here for the model sake we are assuming this to be a different value. So, the shear strain produced there would actually be equal to x by b, because x is the movement and the original distance that was there was b. So, basically if you are moving this lattice from a cubic position or let us say or from a straight position to some angular position, and the distance of movement is x here, this being b. So, shear strain obviously would be x by b, and so stress and strain are related to each other, and therefore, we can say that the total amount of shear stress tau, which is tau 0 2 pi x by a, can be related to the modulus of rigidity or shear modulus times of the shear strain by the simple Hooke's law, and you can say that the tau 0 in this particular case, assuming b equal to a for the lattice, comes out to be equal to g by 2 pi. Okay. So, that is going to be the amount of stress required in order to execute any kind of motion. So, it is going to be actually, you can say, the ultimate shear yield stress value which would be needed for creating the motion which is in question between the atomic planes. You can see that tau 0 is corresponding to the maximum value when probably x is equal to let us say a by 4 or even 3a by 4. So, in that situation the value here for a by 4 would be actually sin pi by 2, which becomes equal to 1, and that for 3a by 4 would be equal to 3 pi by 2, which is again sin pi plus pi by 2, and it is also going to be minus 1. Okay. So, in one case the maximum value of the tau is tau 0, in another case it is minus tau 0, as can be seen from this plot here. So, having said that, it means that the experimentally observed values should at least have same order of magnitude as the g by 2 pi that I formulated in the last step. This is completely untrue. The actual experimental values, as has been recorded, are found to be much less about 100 times lesser than the value calculated g pi 2 by. Okay. So, it is 2 orders lesser experimentally, and this discrepancy is due to the crystal imperfections. You can see, for example, here an extra plane, this is a line dislocation which is available in upper half of the crystal, and so assume that if I put a shear stress, the ease of movement of this already pre-stressed plane would be much more or much easier in comparison to generating an additional plane movement, for example, in the lower half of the lattice. So, you can easily apply a smaller stress and get this misfit plane already to the corner more easily in comparison to what otherwise it would take for a regular lattice without any imperfection. So, in order to just explain this from a real life example, let us actually see what happens to a thick heavy carpet and how we move it, right. So, let us say we have a thick heavy carpet which needs to be moved by a distance delta. Let us say in this direction you want to move this carpet from the point A B to the point A dash B dash, where this A dash is actually delta. Okay. Now, there are two ways to do it. One is that you lift the whole carpet, and move. So, in this particular method you will need much more forces, obviously the carpet is very heavy, being thick and very heavy high density material. So, it is very difficult for you to move it by lifting the whole thing and move. So, there is a simpler way which is there, that you create a kink. So, you can see that there is a kink created in a way that you exactly move delta, and whatever leftover portion you create a kink. So, create a kink and move the kink. So, here probably you can only a single person can do the job. So, you can see that the kink is moving here, and so the kink moves all the way to the other end of the carpet. So, that now the carpet has moved by a distance delta from A B to A dash B dash. So, this is actually the essence of dislocations. So, kink is basically a dislocation. If you create a kink in a particular crystal which is otherwise a regular crystal, it is going to be always easier to move the crystal planes with respect to each other. So, obviously there are a lot more to this, because we are so far being considering only single crystalline orientations, but supposing there is a polycrystalline grain, you already know what a polycrystalline grain is. So, obviously these dislocations are multifarious in nature, and there are many dislocations per unit volume, and whenever you apply a stress they start moving towards each other or away from each other. So, basically there may be a situation where such dislocations are unable to move because they are so densely jamming or packing the way of each other. So, it is like a traffic jam. Okay. So, this also this phenomenon in crystal, particularly polycrystalline material, is known as strain hardening, that whenever you have too much of stress induced into the crystals, because of which this dislocation starts moving in all different directions, they pile up, they jam each other's path, and they are not able to move anymore. Okay. So, obviously the ultimate yield strength would increase because of that. So, these phenomena of strain hardening, etc., we are going to consider in great details in the next module. As of now, I would like to close this module. Thank you.